Alright, welcome back. Here we have another example of graphing a rational function, and we want to pay attention to sort of the difference between graphing a rational function where its end behavior is horizontal or when it's slanted. So we've already done a video where it's slanted. This one is going to be an example of a rational function where the horizontal asymptote, where the end behavior asymptote is horizontal. You've seen this before in Algebra 2, but we want to start drawing our attention to some of the details and how you know right off the bat. But let's go ahead and just kind of start this the way we start any other rational function. We need to factor it. So the bottom's easy to factor. It's x minus 4 and x minus 5. The top, the first thing we can do is take out a 2. That'll to make our life easier. And we're left with x squared plus 2x minus 24. And then we can continue further. The bottom is still x minus 4 times x minus 5. And then the top is, there's that 2 out there, and then you've got x plus 6 times x minus 4. And here you notice that these two factors divide. And do this. A lot of you don't do this. You like stop here, then you get confused. Rewrite what you have left. 2 times x plus 6 divided by x minus 5. Make sure you rewrite it, because this is an easier one to analyze than this. Or than this one, but people forget that once you divide the whole, the factors, they're not there anymore. Okay, so now our zeros. At this point, hopefully you understand that you can get your 0 by looking at the 0 of the numerator. So negative 6, 0 is our 0. Vertical asymptote at x equals 5, because that's what makes the denominator 0. Some students say x equals 4 is another vertical asymptote, but that's not going to be a vertical asymptote, it's going to be a hole. So there's a hole at 4, comma, right? Remember, the hole is like a ghost of a point. So how do we get the y-coordinate of that point? Well, you just need to plug 4 into this result here. Okay, you can't plug it into the original, because if you plug it into the original, you're just going to get 0 divided by 0, because it had that x minus 4 factor in there. So plug it into this one right here. So we'll do that here to the side. 2 times 4 plus 6 divided by 4 minus 5 gives us, the top becomes 20 and the bottom becomes a negative 1. So negative 20. Okay, what next? Well, y-intercept. The y-intercept occurs when you plug 0 in to the function. And we could write it out, but notice what happens. When you plug 0 in, all of this turns into 0, right? And so you're just left with a negative 48 over 20, which would be negative 24 over 10, which would be negative 12 over 5. So our y-intercept is 0, negative 12 over 5. Okay, so far so good. Let's go to the end behavior. The end behavior is limits. As we talked about before, if you want to analyze the end behavior of this, in the long run, we need only analyze the leading terms. So as x goes to infinity, right? As x goes to infinity, the function behaves basically like 2x squared over x squared. Notice that's just, you can divide those x squares, because we're talking about as x goes to infinity, so they can divide because you're dividing big numbers. You don't have to worry about dividing by 0. So that's 2. So as x gets really, really big, the function just approaches 2. So that's one way to view it. In the long run, as x goes to positive infinity, the function approaches 2. And as x goes to negative infinity, well, we didn't even have to plug in any x values, right? When these divide out, all you're left with is a 2, regardless of whether you plug in negative 1,000, a big negative number or a big positive number. So the end behaviors are just 2, the end behavior limits. So that should lead you to assume that the end behavior asymptote is probably y equals 2, and you'd be right. Now there's another way to view that. If you can go through that analysis that we just did, right? And that didn't require really any like calculation, just kind of using your thought process. But we can do it the way we did this, this example here, by using synthetic division, and you'll get the same answer. So like we said before, you can just like you can rewrite. I think I erased it, but 10/4. You can write 10/4 by doing the division. You can write it as 2 and 2/4. We can do the same thing with this guy here. Now let's do it with this representation instead, because that's too terrible to view. Let's just do the synthetic division. So we put 5 in the box. This is 2x plus 12, right? This is really 2x plus 12. So that's just a 2 and a 12. I know this seems kind of funny looking because there's only 2 terms, but watch what happens. Bring down the 2. 2 times 5 is 10. 22, there's your remainder. So that means that this guy here can be also written as 2 plus 22 over x minus 5. And the idea is, as x goes to infinity, what happens to this piece? That goes to 0. So your function just starts approaching 2. So it starts behaving just like y equals 2. Okay, so we have everything we need. So the zeros at negative 6, 0, 1, 2, 3, 4, 5, 6. The vertical asymptote at 5. Whole at 4, negative 20. 1, 2, 3, 4, negative 20. I guess I have to do my scale a little differently. Let's make these go up by 2s. 2, 4, 6, 8, 10, 12, 14. Alright, 2. Well, let's make them go up by 5. 5, 10, 15, 20. There we go. Now I got my hole in there. Whoops. The hole's at 4, negative 20. Sorry. 4, negative 20. 1, 2, 3, 4, 5, 10, 15, 20. So there's my hole. And my y-intercept is at 0, negative 12/5, which is like negative 2.4. So that's roughly here, because remember that's a 5 now since I had to plot that point. So it's there. End behavior asymptotes at y equals 2, so I got to make that like kind of like this now, just because of my scale. But now we've got our graph. It's going to go through these points. Oof, that's terrible. And then again, it's got to be doing this simply because if it wasn't, we'd have another 0. Right? If it was doing that, we'd have another 0. But we know there's only one. So there's our graph.